Okay, good morning, everyone. My name is Geert Leurs. I'm one of the plenary co-chairs of this conference. And it's my great pleasure today to introduce Michal Irani from the Weizmann Institute of Science in Israel, where she joined in 1997. She's there also the Dean of the Faculty of Mathematics and Computer Science. Her research interests evolve around image, video processing, computer vision, artificial intelligence, also decoding visual information from brain activity. I think that's also the topic of the talk today. She got her master's and PhD from the Hebrew University in Jerusalem. And then she was also a visiting researcher at Princeton for 3 years. She received numerous awards and prizes. I'm not going to mention them all, maybe some of the latest ones, which are the Landau Prize in Artificial Intelligence in 2019 and the Rothschild Prize in Mathematics and Computer Science in 2020. She also received several paper awards. Maybe the most prestigious one is the one in 2017, and the Helmholtz Prize, also known as the Test of Time Award for her paper, Actions as Space-Time Shapes. And then also this year she was elected as a member of the Israel Academy of Sciences and Humanities. So prestigious, so congratulations for that. So it's a real honor to have you here, and the floor is yours, so looking forward to your talk. So join me in welcoming Michal.
So thank you for the introduction, and it's a real pleasure being here. It's my first time at EUSIPCO. So I'd like to tell you about some of the work that has been going on in my lab in the past 5 years. But before that, since I'm not very familiar to this audience, I'd like to give a very brief high overview of the kind of topics we work on in my lab. So actually in the last few years, there have been 3 main branches of work in my lab. One has to do with deep internal learning, and I'll explain in a moment what I mean by that. The other is mind reading, which you'll hear more about. And the third is machine reading. And let me say a few words about each of these topics, but I realized I could not cover all of them in a single hour, so I decided to focus on the first 2, which I thought would be more relevant for the signal processing audience. But as I said, I'll say a few words about each of them. So what do I mean by deep internal learning? What I mean by that is how we can train a network, a deep network, in a totally unsupervised way, without ever having seen any prior examples, by training on a single image, the test image alone. Why is this interesting? Well, we're all used to what I call external learning. That is to say, we train networks, we have lots of data provided to us, we train our networks for days, sometimes even weeks, then we freeze the network, and then we apply it to new data as they come along. And this, of course, does amazingly well. We've seen amazing progress in the past decade. But what happens if we don't have enough training data? Well, what happens if the test data is outside the distribution of the training data? In those cases, deep learning fails miserably. And what I'd like to show you today is how we can often overcome these problems by replacing external learning with internal learning. And as you'll see, this gives rise to many applications, including super resolution, spatial super resolution in images, spatial super resolution in video, image dehazing, image segmentation, image retargeting, video and image synthesis, and many more things. I won't be able to explain all of these, but I'll try to give you a gist of some of these things. And then the second topic I will cover is mind reading. How we can decode visual information from brain activity. A person is lying in an fMRI machine, watching images and videos, and meanwhile the brain is being recorded through the fMRI machine. And the question is, can we use those brain recordings in order to synthesize back the images and videos that the person saw? And you'll see that there's a fair progress of this line of work. And here too, we don't have a lot of training data. There's a limited time to put a person inside an fMRI machine, and you'll see how we can overcome that with self-supervision. And the third topic, which is a very new one, and I will not cover today, is mind reading. It started a year ago with our first paper, and the question we asked is, can we decode the data that the network trained on directly from the parameters of the trained neural network. Of course, we're all used to thinking that we can train our networks on data, then we can provide it to someone, throw the data away, and our training data is safe. Turns out that this is not the case. And what we show is in this work is that a fair portion of the training data is actually encoded inside the parameters of a trained classifier, and we can decode them directly from the parameters, not from activations of the network, from the parameters themselves. And this, of course, has severe implications on data privacy. I won't be able to cover that topic today, but I'll be happy to chat about this in the break afterwards, or if I do finish before time, I have a few slides that I prepared that I can share with that. So as I said, I'll focus today on the first two topics, which I thought would be more interesting to the signal processing community. And let's start with the first one, deep internal learning, how we can train a network on a single image. Well, of course, you can ask, is there enough data, how we can train a network on a single image? Well, it turns out that there's a lot of redundancy inside a single natural image, both within the original scale as well as across different scales. When I say within the original scale, what I mean is if you see a small patch once inside the image, you'll almost surely see it many more times inside the same image. Here I'm showing you large patches just for visual purposes, but in practice I'm talking about much smaller patches, 5 pixels by 5 pixels or 7 by 7. And this property has been used by us and by many others over the past 2 decades for lots of applications, including image completion, image denoising, non-local reads, which you're all familiar with, visual summarization, and more. But it turns out that the recurrence of patches is not only within scale, but also across scales. That is to say, if we take the image and scale it down, then almost any patch in the original image will almost surely have an identical patch in a coarser version of the image without scaling down the patch, which means that tiny patterns appear in multiple sizes in the original image. Again, I'm showing here large patches, I'm talking about much smaller patches. And again, this property has been used by us and by others for lots of applications, fractal image compression, super resolution from a single image, blurring, denoising, and dehazing, and many more. Now, this may look like a contrived image to you, and you can ask, well, does this go beyond such images with such clear repetitive structure? And the answer is yes. If you go to small enough patches, 5 by 5, 7 by 7, it's true for almost any patch and almost any natural image. For example, if I show you this image without any clear repetitive structure, then if we look at the patch along the edge, then it will appear many, many more times along the same edge. And similarly, across scales, okay? Edge patches will repeat across scales, even though they're not scaled down. And similarly, corner patches. So you can say, okay, repetitive structure, edges, corner. What happens if I go to unstructured picture like this? Does this still hold? Well, let's zoom into this picture. And you can see that locally we have very similar type of structures, okay? And we showed in our 2009 paper that this natural image had this very, very strong fractal-like property, okay? This strong recurrence of patches is true for almost any patch in almost any natural image, indoor, outdoor, man-made, or natural. So as I said, this gave rise to lots of applications by us and by others over the past 2 decades. And the nice thing about this property is that it's totally unsupervised. It serves as a very, very strong prior for solving ill-posed problems without needing any additional examples, okay? You just have to solve the problem subject to maximizing this internal recurrence of patches. The bad news is in the last few years, this has been totally overcome by deep learning, which is very impressive, okay? So for a while I wasn't impressed about this, but then I said, okay, if you can't beat them, join them. So let's say on one hand, we have this deep learning, which is amazing, does amazingly well, but it's really, really data hungry, and we don't know what the network is really learning. On the other hand, we have this strong internal redundancy, which is a very nice physical property. We understand it, and it's totally unsupervised. It doesn't need additional examples, but doesn't perform as well as deep learning. And the question I was asking, is there a way to combine these two complementary ideas? And luckily, 5 years ago, my former PhD student, Asaf Shapel, came up with the idea of doing deep internal learning. That is to say, let's train a deep network in a totally unsupervised way, without ever having seen any prior examples, by training an image-specific CNN at test time on examples extracted from the test image only. Okay? And as you'll see shortly, this can actually be done quite efficiently. So the first problem we looked at was that of super resolution using deep internal learning. That is to say, we have a low resolution image. The goal is to increase the sampling rate to generate a high resolution image, but we don't want to just interpolate the image. This is what you see here. That's not interesting. It doesn't add any new information. We want to be able to recover information that is smaller than a pixel size, that is not visible in the original image, that goes beyond the Nyquist limit of the original sensor. And there are, of course, lots of work on super resolution, but by far the current leading methods are those based on deep learning, or what I call external deep learning. So the idea is that in external deep learning for super resolution is let's train a network on lots and lots of pairs of high resolution, low resolution images. The network will receive the low resolution image and will learn how to output the high resolution image. And of course, you can have as many training examples as you want, because all you have to do is take a high quality image, downscale it, and you have such a pair. And so these initial networks came out, and they trained the networks on lots of images for days, maybe even weeks, then froze the network, and then you could apply it to new images as they came along and get a super result image. This did amazingly well. In fact, when it came out, it immediately gave a jump of 2dB and PSNR beyond anything classical that existed before that. But when Asaf and I checked it, we found out that these networks work well only under ideal conditions. What do I mean by ideal? After all, we generated the low resolution images from the high resolution images by downscaling them with some predetermined downscaling function, usually an ideal low-pass filter or a good bicubic downscaling kernel. Well, it turns out that these networks worked really well on ideally downscaled images, but once you took them out of their comfort zone to images that are not ideally downscaled, they didn't do any better than interpolation. And you know what? The world is not ideal. When I take a picture, I slightly move my hand. The picture looks good to you, but there's a slight blur there. It's not an ideal low-pass filter. And when I'll take another picture, it will be a slightly different blur. This downscaling kernel is not camera specific. It's not even photographer specific. It's image specific. And when you apply these kind of networks to those images that were downscaled non-ideally, they didn't do any better than interpolation, and I'll show you shortly. So we said, okay, let's replace those external learning with internal learning. Let's adapt the network to the image-specific degradation of the image-specific data. And our idea, we called it zero-shot super resolution, or in short, ZSSR. It's not a nation. The idea is the following. Here's your low resolution image. That's the only information you ever saw. You've never seen any other image in your life. What we'll do is the counterintuitive thing. We will downscale this image even further to generate an even lower resolution image. And in a moment, I'll say how we downscale it. And then we'll train a light network to learn to upscale this image back again. And the loss is, please return back to the original image. And once you train this network on this image, you can now apply it to the original image to generate the super result image. And the rationale here is because we have this strong recurrence of patches across scales in the original image, then whatever network learns how to increase the resolution of tiny patches in the original, in the tiny image, will also know how to increase the resolution of patches in the original input, low resolution input image. Now, of course, training a network on a single pair of input-output is stretching it too much, so we applied augmentation to the input image. We flip it, we rotate it, we scale it, and generate such hundreds of pairs of low-resolution, high-resolution pairs of examples on which we trained the network. And this gives us an image-specific CNN, and because it learns to super resolve only this particular image, it trains only on the patch distributions coming from this particular image. It's a very light network, and therefore it's a small network and can be trained and applied within a few seconds on a V100 GPU. Now, what about the downscale? We said that changes from each and every image. We said the degradation is image specific. Well, it turns out that the ideal downscaling, the one with which the original image was generated, can be also extracted from the original image. The correct degradation is the one that if you downscale the image with it, will maximize the similarity of patches across scale in the original low resolution input. We have an analytic proof of that in our 2013 paper, and and also a method that we developed using deep internal learning in 2019. And I will say a few words about this a few slides down the line. But let me first show you results. So this gives us really super resolution in the wild. Okay, it adapts itself to network to any data type, to any kernel that you can downscaling, and to any aspect ratio that you want. So let's look at some results. Here is a low resolution image with an unknown downscaling. It looks okay. Here is its interpolated image. You can see it's slightly blurry, but it's okay. Here's what happened when we applied the external state-of-the-art at that time, external super resolution, okay, the state-of-the-art. And if I flicker between the two, you'll barely see the difference. Nothing is wrong with your eyesight. Now, EDSR Plus is a wonderful algorithm, as long as it's applied to bicubically downscaled images. But once taken out of its comfort zone, it doesn't do any better than interpolation. Here, in contrast, is the result of ZSSR, the internally trained super resolution. And if I'll flicker between the two, you'll see the dramatic difference. We're able to recover fine details. And the only reason we're able to do this is because the network adapts itself to the image-specific degradation and the image-specific recurrence of patches. Another example, an old photo we downloaded from the internet, Checkpoint Charlie, just shortly after World War II. You see the wall hasn't even been built yet. We have no idea how this image was generated. Here is interpolation. Here is EDSR Plus, the externally trained super resolution on that image. Again, if I'll flicker between the two, you'll barely be able to see the difference. And if I'll now apply the internally trained super resolution, this is the result. And let me flicker between the two, and you'll see the dramatic difference. You can see the, for example, look at the leg there. You can see the gap. I don't know if you can see my cursor. Can you see my cursor? Yeah. You can see the gap between the two legs, or the edges of this thing, or the bikes here at the back, the motorbikes. It really recovers information smaller than a pixel size. It goes beyond the Nyquist limit. Okay? And this is simply because it exploits the internal recurrence of patches and the image-specific degradation. Another example. Okay. This is a JPEG compressed image. It looks okay. If you super resolve it with the EDSR Plus, it super resolves both the signal and the noise. Okay. It doesn't know the difference between the two, so it tries to super resolve both. In contrast, here is the internally super resolved, and again, if I'll flicker between the two, you'll see the difference. Well, how come? We don't train it to we don't know what the noise is, but the signal patches have this nice recurrence across scale. The noise patches do not. So the network sits and trains in lots of augmentations of the image, learns how to generalize for the signal, but it doesn't know what to do with the noise, so it ignores it. And of course, in the paper, you can find many more results and empirical evaluations. Let me just say that on ideally downscaled images, we don't do as well as the external methods. It's their bread and butter, they do much better. Okay, we do reasonably well, but we're not state-of-the-art there. But once you take them out of their comfort zone to non-ideally downscaled images, or even to ones with noise, we showed a gap of 1 or 2 dB compared to previous methods, at least at the time of our publication, which was several years ago. Now, what about the kernel? Remember, I said that the downscaling has to be different for each and every image, which is one of the problems with the externally trained ones. What do we do then? How can we recover the kernel blindly from the low resolution image? All we have is the low resolution input image. We don't know what the high resolution image is, nor what the blur kernel with which this image was blurred before downscaling was. Okay, and we need that in order to downscale our image to train the ZSSR. Well, it turns out, and we showed this analytically in our 2013 paper, together with Michal, that the correct downscaling kernel with which the low resolution image was obtained is also the one that, if you downscale the low resolution image with it, will maximize the similarity of patches in the image with their nearest neighbors in the downscaled image. And in the 2013, apart from having a proof, analytic proof that this is correct, we also posed this as a well-defined objective function and solved it with non-convex optimization using iterative alternating optimization. But more recently, in 2019, we found a way to recover this downscaling blur kernel directly from the low resolution image using deep internal learning. So let me say a few words about how we do that. Here is your low resolution image. Again, that's the only image you ever saw, and you want to recover the blur kernel that was used to downscale this image, to generate this image. Well, what we'll do is we'll train a GAN, a generative adversarial network, to complete this kernel. And the generator of the GAN will actually be the correct downscaling kernel. It will learn how to correctly downscale the image. Now, what is good downscaling? As I explained, the good downscaling is the one that will maximize the similarity of patches across scales in the original low resolution image. How can we guarantee that the generator generates the image this way? Well, what we'll do is we'll train a discriminator that will sometimes get crops from the original low resolution image, and sometimes we'll get crops from the generated downscaled image. And we'll try to tell the two apart. It will generate for each patch, it will say whether it came from the original patch distribution or from the generated patch distribution. Now, again, as it trains, the discriminator will try to get better and better at catching the generator and knowing the difference between the two. The generator will try to get better and better at fooling the discriminator so it cannot distinguish between the patches of the original image and the downscaled one. And when the GAN converges, the generator will converge to the good downscaling kernel that maximizes the patch similarity between those two images. And now note that the generator cannot be just any deep linear network. If it's a deep linear network, it can also generate a garble of patches. It can, for example, do a mode collapse. The discriminator will be happy because all those patches came from the original patch distribution. The generator will be pleased because it fooled the discriminator, but this is clearly not what we want. Okay. The generator has to satisfy this expression. It has to be of the form of blur and subsampling. Okay? Or in other words, it has to be a linear operator. So the generator cannot be a regular deep network. It has to be a linear network. Okay? And so we said, in fact, all it needs is a single convolution kernel, right? That's what we wanted to model. So we said, great, let's replace the generator with a single linear layer, with a single convolution kernel, and we're done, right? Well, it turns out that this worked horribly. Okay, it failed miserably. If these were, for example, ground-proof downscaling kernels, here's what the generator managed to converge. Now we couldn't figure out why this was not working until we realized that here is the issue, right? Deep learning does amazingly well, but the reason it does so well is that there are no local minima, right? You initiate a network with random weights. Each time it will converge to different weights, but all of these are equally good. Okay? Each time you train a network, you start with random weight, random weight. It will converge to different types of weights. All of these will be equally good. Deep learning was shown to not have any bad local minima. But this is not the case. Okay, oops, sorry. It's not working. Why is this? Okay, never mind. This is not the case here. In our case, we have a single good global minimum. Okay, the kernel that we're seeking. Okay, there's no multiple good local minimum. Okay, we're only seeking this one single kernel with which this image was maximized. Now, the error surface of the generator is non-convex, right? It doesn't only have to solve for this linear downscaling. It also has to fool the discriminator. This is a very complex loss. This is a very complex error surface. And when we initiate the generator with random weights, it has no chance of converging into this single global minimum. Okay? And so we realize that there's no chance this will work. Turns out that what does work is replacing the generator with a deep linear network. What is a deep linear network? It's a deep network, but with no nonlinearities, no activation functions, no values whatsoever. And when you multiply all the weights from all the layers, you get the correct kernel. So it sounds strange, right? It sounds completely identical. Is there a difference between the two? Well, there's a big difference. And the difference is that this single layer network has only a single solution for the generator weights, whereas this network, the nonlinear one, has infinitely many possible weights. It has infinitely many decompositions of the kernel into different weights across different layers. For example, if this, for example, is a good decomposition, then if you apply one of the layers with a matrix A and the other one with the inverse of A, it would still compose into this single kernel. And you can do it with any invertible matrix A, and you can do different matrices between different layers. In other words, you have infinitely many good local minima to this deep linear network, all of which will generate this single kernel. And it turns out that this solves the problem. So these were the original ground truth kernels, and this was the single result of the single layer generator. Those were the results of the deep linear generator. And as far as we know, this is the first ever practical use of deep linear networks. Okay, theoreticians have been using this to prove things and so on, ignoring the activation because it made their proofs easier. But it turns out it also has some practical applications. In fact, I believe it can be used for solving with deep linear networks any linear problems subject to nonlinear primers. All right. So far I showed you how we could use deep internal for doing super resolution. The nice thing about it, totally unsupervised, doesn't require an acquired example, it adapts itself to the image-specific degradation. There's no notion of being alpha distribution. Any image has its own image-specific CNN. But then we asked ourselves, can we use it for other things? For example, for segmenting an image into its foreground and background layers, for separating an image with transparencies into their reflection and transmission, for taking an image taken under haze and dehazing it, generating images if they can under good weather conditions. And it turns out that all of these can be solved using deep internal learning in a totally unsupervised, with no prior example, by training on the single image with an image-specific CNN. I won't go into the details of this because I have no time, but if you want to find out more details, you can look at our paper on double fit. Let me say just a few words. Once you separate the image into two layers, each one of those layers has a simple distribution of patches, simpler distribution of patches, simpler entropy of patches. So we train a pair of deep image priors so that their sum gives the original image. And those networks, since it's easier for them to generate the simple distribution of patches, they tend to split the patches between themselves. And this is how we get this result of the unsupervised way. We've also trained again on a single image, not only to find out the downscaling kernel, but also in order to do image retargeting, generate diverse images from the same patch distribution. And those of you who are familiar with SynGAN, this actually predated that. The idea is we train a generator to learn the patch distribution from a single image, and the generator, of course, can then generate new images with different sizes and different aspect ratio, but all of them with the same patch distribution, so that the discriminator, when it looks at crops from the image, from the generated image, cannot tell them apart from the original input image. And this allows us to do image retargeting, and let me show you a few examples. So this is an input image, again, is trained to learn this distribution, and once it learns, we can generate a whole variety of images with different sizes and aspect ratios. But note that although we change the aspect ratio of the image, the aspect ratio of the patches do not change. The fruits remain the same size and aspect ratio. All the elements remain the same. It just makes 3 rows of watermelons. It adds boxes of fruits and so on, but it all comes from the same patch distribution. Or similarly, the penguins don't get any fatter, just more and more of them are born. Or similarly, for the poles in the temple, they don't get fatter, it just generates more and more of them. Okay? And of course, no one's perfect. India doesn't know anything about objects or scenes. All it models is the patch distribution at multiple scales of the image, so it can easily generate that kind of an image. But if you were to generate a larger image, it will now split it into 2 people. That's what would have also happened in the penguins. If you stop it, freeze it somewhere in between, you'll see it 2 penguins combined like this. Because locally, for the discriminator, this looks fine. Of course, we all know that more recently, diffusion models were shown to be stronger generators than GANs. And so, of course, we tried to train a diffusion model on a single image or a single video. And this is a very recent ICML paper from last month. Again, I won't go into the details due to the interest of time, but given an input video, again, we trained the diffusion model of crops taken from the input video. It learns to generate the patches of this particular image from pure noise, as well as the emotions. That's what we trained the diffusion model to do, given different crops and augmentations of the input video. And then we can synthesize new videos, all coming from the same patch distribution and motion distributions. But we can do many more things. For example, we can also extrapolate the video, and I'll play it in a second, but let me say first, extrapolate it both forward and backward in time into the future or into the past. So when I'll play this, please note the frame, the color of the frame. Red frames mean the original input video, and when you'll see green frames, those are interpolated, those are extrapolated frames that were generated by the diffusion model. So the red ones are the ones that the diffusion model trained on. So again, this is a tornado, 30 frames, and now you can see already extrapolated frames into the future. Again, red frames are the input, green frames are the generated ones. And so we can synthesize it to the future, or we can extrapolate into the past. We can play it backwards, and backwards in time. By the way, the numbers that you see here are the numbers of frames. So negative frames means before zero, before the beginning of the video. Okay. And similarly, we can do the same for the balloons. Okay. Again, red frames are the original input frames, and then green ones are the synthesized one. These are many possibly different pasts, starting from different noises of this input video. And you can see that it generates hundreds of frames away from the original input video into the past. You can see that it synthesizes clouds, and forget red frames, green frames. It synthesizes the motions of the clouds and gives birth to more and more balloons coming down. All of this from the same distribution of input video. Okay, so let me finish here with the first part. I've shown you how we can combine deep learning with image-specific to generate image-specific DNNs, what we call deep internal learning. We combine the power of deep learning with image-specific internal priors. The nice thing about it, it's totally unsupervised, requires nothing but the input image or video, and adapts itself to the unknown image-specific conditions and degradations. And it has many applications. The nice thing about it, there's no notion of being out of distribution. Of course, future questions. Can we assign it to other types of domains and signals, audio, medical imagery, EEG? These are all interesting questions. And can we combine the power of internal learning and external learning and generate a continuum between the two? Right now we have two extremes. Either we train things to death, freeze, and then apply to new data, and we don't know what to do when things are out of distribution, or when we don't have enough training data, or we have internal learning. We train a network from scratch on a new image or video each time. Can we generate a continuum between the two, namely train on as much information as you have and still do something sensible? So let me move now to the second part, mind reading, and it's based on three papers of ours, Europe's 2019 Euroimage, and then the recent archive one. And the main paper behind this work are Mohamed Bailey, Guy Gazir, Nicolas Note, and Benit Kugelschmidt. So what do I mean by mind reading? Well, the person is lying inside an fMRI machine, watching images or videos, and meanwhile the brain is being recorded. We look at the area of the visual cortex, and the question is, can we use those recordings in order to synthesize back what the person saw? Synthesize the images or the videos that the person saw. Why is this interesting? Well, they give rise to brain-machine interfaces, allow us to communicate with locked-in patients, explore dreams, study consciousness. These are all very good goals. We're not there yet, but let me show you the baby steps we have taken in those directions. Now, of course, the problem is not new. It's been explored by computational neuroscientists for more than a decade now, starting with the famous works of Gallant and Kamitani, and of course, there are many other famous scientists working on this, like Naselaris and Kay and so on. And the problem they pose is, they assume that they have pairs of images and their corresponding fMRI recording. And the question is, can we learn to decode those fMRIs into those images? But when we encounter a new fMRI of never before seen images. And in the initial older works used linear regression methods between handcrafted features, and more recently deep learning has come into play. But the problem is there's not enough training data. There's a limit to how much you can put a person inside an fMRI machine. And so the types of data sets, we don't accumulate the data, we download them from the internet. The types of data sets we had were limited, for example, to 1,200 pairs of images of their corresponding fMRI, which is far to span the huge space of natural images. And it changes from brain to brain, so it's not like you can have this person see the 1,000, those 1,000 different person. And the signal-to-noise ratio is very poor. In fact, it doesn't even measure electrical activity of neurons, it just measures oxygenated blood flow, right? There's oxygen is flowing to areas where the brain is active, and that's what it measures. So we said, okay, let's try to overcome this limitation using self-supervision. And so our idea is the following. Let's train two networks. The first network, we'll call it a decoder. We'll learn to decode fMRIs into images. This is the network we will eventually use in order to decode the new fMRIs as they come along. However, if we train this network only in the supervised ways on those 1,200 examples, it will just overfit the training data and will not generalize well to new data as they come along. So what we do is we also train another network in the opposite direction. We'll call it an encoder. It's a network that learns to encode images into their fMRI, a slightly easier direction because we go from good quality information to low resolution, but still not trivial. But here is where the trick comes in. We add self-supervision. What we do is take any image, an image without any fMRI, okay? What we'll do is if we apply our encoder to it, it will generate some pseudo-fMRI. And if we apply the decoder to that, it will generate some garbage image because it never saw this fMRI before. But we know that if trained well, this back and forth should lead us to the same input image, right? It should be cycle consistent. And if we enforce this on the output, then we can use that in order to improve the weights of the network, especially those of the decoder. Now note that this can be used with any image without any fMRI, which means we can train it on as many images as we want. In fact, we trained it on 50,000 ImageNet images. Okay? And this allows us to adapt the weights of the decoder to the statistics of natural images, images that were never seen inside an fMRI machine. But by the way, we don't just compare the pixels at the input and output at the pixel level. We also impose perceptual similarity. For those of you who are not familiar with it, you just apply the input and output into pre-trained image classification network, and you expect not only the pixels to be the same, but also intermediate levels of the deep network, the features generated from those images, so that now it also imposes higher level semantic information between the input and output. And this allows us not only to adapt the decoder to never before seen images, but also to never before seen classes inside the fMRI. But we can do more than that. We can switch the order of those two networks. Now, the input is an fMRI and the output is an fMRI. And if trained well, those should be equal, which means we can apply it to fMRI without any images. And specifically, we can apply it to the test fMRI, which we want to decode. We have to induce this consistency on the test fMRI, which means we can adapt the decoder to the statistic of the new test data, even if it's outside the distribution of the training data. Okay. Now, of course, there are issues here. We have to make sure this is not just an autoencoder. We have to make sure we pass through real fMRI space, and we do that by not allowing them to train together. You can find out many more details in our neuroimage paper, but let me show you the results. So here is an input image, and that the person saw inside an fMRI machine, and here is the reconstructed image from the fMRI. So this is a goldfish, or a whale, or an airplane, a snowmobile, some outdoor scene, a llama, a beer mug, tambourines, and many other images. And you can see that sometimes it recovers better, sometimes worse, and sometimes it fails to recover the color. But all in all, of course, I'm showing you here our best results. We also have horrible results. These are the worst reconstructions at the bottom there from the test data. But all in all, on those two datasets that we worked in, we showed that we have state-of-the-art reconstruction results, and this was evaluated both by human raters as well as by objective measures. You can, of course, ask, well, how does it compare to other methods, for example, GAN-based methods? Okay. So what you see here on the left is the ground truth. In the middle, the column in the middle is our results, and on the right is results of Sheneka from Kamitani's group. And they use a GAN-based method. And of course, a GAN-based method, their images are visually very pleasing, much more pleasing than ours. Okay. For example, look at this teddy bear. It looks amazingly well, but it's unfaithful to the underlying fMRI, where it's not supposed to be a teddy bear, it's supposed to be a llama. Okay, so the GAN generates really beautiful images, but they're not necessarily faithful to the underlying fMRI. Or for example, this beautiful image. Beautiful, but doesn't look like a butterfly. And here is a different data set and a different method. The ground truth is on the left, the middle is ours, and the right is Sandeep et al. From Asilai's group. And in both, once again, they use a GAN-based method. In both data sets, we compared to the both data sets to the methods that worked that proposed those data sets, and we showed superiority. And by the way, there are now new data sets with more training data that use diffusion models. We're now looking into that. Again, they generate very nice images, much better than these GAN-based methods, but again, they're not always faithful to the underlying fMRI. We're now looking at how to combine these diffusion priors with our own method in order to generate good outputs that also are faithful to the underlying fMRI. And of course, you can say, well, can we not? So far, I showed you how we can synthesize the images from the fMRI, but it's not always easy to say what it is you see here. Can we also classify them, say that this is a fish, this is a fly, and so on? Now, this is a very, very challenging problem for several reasons. First of all, the test classes are mutually exclusive from the training classes. All the 1,200 pairs of images in the corresponding fMRI came from training classes that are not, and the test classes are new ones that are different from the ones that training data has. Also, we cannot use pre-trained image classification networks for two reasons. One is most of the classes in this test set, 30 out of 50, are not part of 1,000 ImageNet classes. So we cannot apply pre-trained image classification that were trained on ImageNet because it doesn't know these new classes. And secondly, even the classes that it does know, it will be difficult for it because those reconstructed images of ours look very different from real natural images. They're outside the distribution that those networks trained on. Yet, we pose ourselves a very challenging goal. We want to classify our reconstructed images against 1,030 ImageNet classes. Why 1,030? 1,000 ImageNet classes plus the 30 missing ones that there are from this test data. That's how we came to the 1,030. This is a very challenging task, and as far as we know, nobody has ever attempted such large-scale classification from brain activity. People use two-way, four-way, cheating, lying, not lying, say the truth, two-way, four-way, eight-way. Nobody has ever tried such 1,000-way classification. So let me show you how we go about doing that. So here is our decoder, the test fMRI, and the reconstructed image. What we do is we pass this reconstructed image into a pre-trained image classification network. And we take the fourth layer. We said it doesn't know those particular classes, but we take an intermediate layer, the activation, the node intermediate layer, the features there, as a signature that represents this image. And we now look for its nearest neighbor among a gallery of 1,030 signatures, one per class. How do we generate those signatures? The way for example, if you have a class, let's say the tiger shark class, here's such a class in the ImageNet. We randomly sample 100 images from this class, generate the signature of each one of those images by passing it through the network, and then, parsing two things at the same time. Okay, we're generating the signature for each one of those images, and then taking an average of these. And this generates a single class representative, one out of this 1,030 classes. And now, given a new fMRI, we decode it, we generate its signature, fourth layer in an AlexNet network, and then we look for its nearest neighbor among those 1,030 class signatures. And we can say here is the best class, here is the second best, here is the third best. We can do more than just classify, we can also rank all the classes according to how well they represent this image. And as I said again, the 50 classes in our test data are all new classes. They were never seen at training time. They're not part of the 150 classes in this 1,200 pairs of supervised training data, nor are they, remember I said we also train on cycle consistency on new external images which have no fMRI. We made sure that these do not come from those particular test classes also. So the test classes were never seen at training time, yet we get 12% top 1 accuracy, which is more than 100, is more than 2 orders of magnitude the chance level. And you can ask, well, is 12% good or not? Let me show you visually and you can judge for yourself. So here are examples. On the left, what you see is the ground truth images with their ground truth class labels written in red above them. The second column shows you our reconstructions, and what I'll show you now are the top 5 classes for each one of those images that were found out of those 1,030 classes. So for example, let's look at the first row. What you see here, these are the class labels that it gave, and in each one of those you see a random image from this class, just to give you an idea what this class is about, because sometimes those names tell us nothing. So as you see, the first image was classified as a housefly. Indeed, it was ranked number 1, at least the correct class, but if you look at the other 5, they also make a lot of sense. The cicada looks like a fly, and in the 5th place there is a fly class. It turns out that fly and housefly are different classes. Okay. Or the second row, we ranked airliner number 1, which is correct, but then the second place we found the warplane class, and also in other places we found other vessels. Similarly, stained glass is ranked number 1, but look what it found in the other top 5. Vending machine, slot machine, altar, they all look visually quite similar. Okay. Or the beer mug was ranked 1, but then it found the coffee mug. And duck is an example of a wrong classification. It's a swan, it's not a duck. That was ranked number 1. But in the 4th place, it found the swan. Okay? So these are very difficult tasks, okay? And let me show you visual examples. So as I said, in 12% of the cases of the test examples, the correct class was ranked number 1 among a gallery of 1,030 classes. But let's look at examples of wrong classifications, where none of the top 5 had the correct image classification. So image class. So here is such example. So the llama, there's no llama in the first 5, but they're all furry white animals. Or the leopard is not in the top 5, but there is a lion in the 5th place. A camel is not in the top 5, but look at the 2nd place. There is a class called Arabian camel, which is different from the camel class. So it found that. Wrong classification, but I think you wouldn't be able to tell the difference either. Canoe, didn't find a canoe, but it found a paddleboat. And goldfish, it didn't find, but it found other fish. So even the wrong classifications make a lot of sense. Okay, and the last thing I'll show you, and with this I will conclude my talk, we recently extended this for video classification, a video reconstruction from fMRI, not classification, sorry, reconstruction. Now, this is a much more challenging problem. It's a much more difficult problem. fMRI, we have a sample once every 2 seconds. Video is 30 frames per second. So we're going from 30 hertz to half hertz. Okay? Or in other words, every fMRI, every 60 frames are folded into a single fMRI. Before, from each fMRI, I wanted to reconstruct a single image. Now, from each fMRI, I have to reconstruct 60 frames. We don't do that. But we do reconstruct the video at higher frame rates than the original fMRI sample rate. We reconstructed either at half hertz, which is the original fMRI sample rate, but also at 1 hertz, 2 hertz, and 4 hertz. I won't go into the details because of the interest of time, and I have to finish, but it's an extension of our image-based decoding method, again, 2 networks, encoder and decoder, but they now have also a temporal component, and of course there are other intricate details that have to do with the fact that it's video, and you can find more details in our recent archive paper. But let me show you results. So I'll play this in a second. At the top, you see the ground truth video. At the middle, you'll see reconstruction from the fMRI of one subject that watched this video, and at the bottom, you'll see reconstruction from fMRI of another subject that saw the same video. And again, remember, It's a much more challenging problem, so don't expect to see good reconstructions like I showed you with the images, but you'll see that it is able to reconstruct rough shapes, able to reconstruct the dynamics, and sometimes even colors. So let's look at that. And you can see how, but again, these are videos we downloaded. You can see again how erratic the data is. Every few seconds there's a scene cut or scene change, which means that every fMRI, which is only once every 2 seconds, often has information from 2 totally different clips, which makes the problem even more difficult. But that's the kind of information we had. And again, very limited training data, so we need self-supervision on videos which have no fMRI for these. All right, so let me finish my talk and summarize. So in the first part, I show you the idea of deep internal learning, how we can combine the power of deep learning with internal and specific priors. As I said, the nice thing about it, there's no notion of being out of distribution, no need for prior training examples. And the question is, can we dive to other signal types and domains? And can we define continuum between internal learning and external learning? This is a very interesting question. And the second part, I showed you how we can decode visual information from fMRI brain activity. And what made it work is the self-supervision on images without fMRI, fMRI without images. This currently, these are the datasets we check, gives state-of-the-art image and video reconstruction and classification. And of course, there's a good question, can we use this to decode dream of the person sleeping inside an fMRI? Not yet. Can we combine information from multiple brains? Use one brain to improve the encoding of another? Actually, this is ongoing work and we have good results there. Can we learn new information about the brain? What is encoded where? Using our encoders to figure out those things. Again, this is something we're looking at. And one of my dreams is to extend this to speech decoding from brain activity or maybe even from EEG. Wouldn't it be great if we could communicate with ALS patients, have them think what they want to say and voice it out? But again, this is something we haven't started doing yet. And just to mention again, there's a third line of work going on in my lab, very recent ones that started a year ago, how we can reconstruct the training data directly from the parameters of the training neural network. Again, this has severe privacy issues, and it turns out that the answer is often yes. But you can, if you want to find out more details, you can look at our recent emerged paper. So thank you for your attention, and I'll be happy to take questions.
Questions? Yes. We have a microphone.
First of all, thank you very much for this very beautiful presentation. The form, in the shape, and in the contents was wonderful. I have a lot of questions. I will be happy to discuss with you after the talk also, but I guess 3 small questions, okay, possible. First of all, if for the first part, when you have a lot of data which is available, is this still worthwhile to try internal deep learning, or external is always better if you have more data? That's the first question. The second question also related to the deep internal learning. If I understand well, you need one model per image. And when you start with another image, you have to develop another model. Even if it is not a very complicated issue, but you need one model per image, is true. And my last question about the video reconstruction, getting the past or the future, I guess you compared with the true history of the video before and after, and I would like to know what is the result of the comparison between your inspection of the history, these are the past and the future, with the true history of the video.
Okay, I'll try to remember three questions as we go along. Regarding your first one was, does it always do better than external? And the answer is no. Of course, external data in learning, if you have good training data, it will do, there's no, look at us, we learn a lot of data and we use it, okay? There's no notion of being completely ignorant of what you know, okay? But those deep learning methods, if they don't have enough training data, they don't perform well. Okay? And what happens when you don't have enough training data? And that's what I meant when I said generate the continuum. It's not, let's train on lots of data and then only fine tune on a single image. My question is really, I mean, we humans, when we see when you show a child 3 images of a cow, some of them have maybe even pictures or cartoons. It recognizes a cow when it sees one. It doesn't need 1,000 images of cows from all different orientations, with all possible augmentations and all possible dogs, in order to recognize a cow. Okay? So there's a gap, and we humans, we can gradually learn using as much information as we have.
So you see gradiometer is closer to what the brain is actually doing.
I don't know what the brain is doing. I'm not a neuroscientist, although I do work on brain reconstruction. I'm not a neuroscientist, okay? But the thing is, it's obvious that deep learning is not doing what the brain is doing. It doesn't know how to generalize from few examples. It only interpolates between the examples that it receives. And in order for this interpolation to be sophisticated, to be good, it needs lots of examples. It doesn't extrapolate. It doesn't go beyond the convex Holland way, if you want, of all its training examples. Okay? And we humans do that. Okay, so it's not the same. And that's my question about the continuum. Can we generate a continuum between internal learning and external learning? And in deep internal learning, we generalize from nothing. Okay? And the question is, can you learn from as much examples as you have? You have one, learn from one. You have three, learn from three. You have millions, learn from millions. Of course it will be better than learning from one. Okay? Your second question.
One model per image.
Yes, that's currently what we have, and that's exactly why I asked, can we generate a continuum given as much information as you have? I mean, right now, we're completely ignorant. We start from scratch. Now, if you take externally trained ones and try to fine-tune them on the particular new example, it doesn't work. They're already stuck in this deep global minimum or local minimum. It's very difficult to get them out of there. Okay? It's not just like that. And the third one was
comparison between.
There's no single real good past. Okay, depends. I mean, there is one real past, but there could be infinitely many good pasts. That's what we're generating. We cannot compare to the real past because each time we start with random noise, different random noise in the diffusion model will lead you to a different solution. But it has to be a plausible solution given the input.
It's a probable solution, but not. It has not to be the true solution.
Yes.
One possible.
The true solution is one plausible solution, but there are many others.
You are not getting the past or the future, actually.
Maybe one of them is the true.
Thank you very much.
Yeah, fascinating presentation. Thank you very much for that. With respect to part one, I guess even with looking at the first bullet item there, do you have a good working definition of the signal type for which the internal learning works well?
As I said, we need some strong recurrence of information inside. Those you have to be your atoms, your elements. In images, we found those, and so when we model our image-specific network, we make sure that each output pixel, for example, in super resolution, it's the area that it looks at. What's the word? It's receptive field. The receptive field of each output pixel is of the size of a small patch, and that's why it works there. Okay, you have to find this repetition. I'm sure it's also in audio. I'm sure it's also in any structured signal, which is not random. I'm sure you can find elements that repeat. But you have to find the good size and or which on one hand is not trivial. Of course, pixels, a single pixel will repeat itself, but it's not indicative of anything. And if you take a huge thing, if you look for correlations for that, if you find something like that, that's great, but you're unlikely to find many repetitions of it. And so the reason we go to 5x5 or 7x7 patches is that finding correlations of those is indicative enough to be meaningful to predict something. Yet, it's small enough to repeat. Okay? And those are the elements that you have to find when you try to generalize it to other signals.
Okay, and just maybe a brief follow-up on that. But like if you take, so if you took these images and just permuted the pixels, would you get good results still?
No, because you wouldn't have this nice. If you just randomly permuted pixels,
but you could
like
change the domain. You could change the domain of the kernel, though, right?
I'm sorry.
I mean, it seems like the repetitive structure would still be present in the image.
No,
would be
what size? But what size? If you just permute pixels, the repetitive structure would be of the size of the pixel,
yeah,
not the size of the patch. As I said, that's not indicative. It's not generalized from that.
Thank you.
Other questions?
Thank you. Very interesting. I've got a question which is about part 2 and the image reconstruction, which is kind of analogous to your first part, the problem that you were dealing with. If the human subject has not got familiarity with the image that they're being shown, for example, a small child who's never seen a cow before but is familiar with dogs will first call the cow a dog. How does that sort of subject personal experience in image, like image observations and subjects, come through in the fidelity of the results in the reconstructed images?
You're asking about the reconstruction from MRI?
Yes, please.
I have no idea. Look, these were all grown-up subjects, so I'm sure they're familiar with the visual world. That were not random people or children. You're asking whether fMRI activity, I assume it will be different when you encounter something you've never seen before. You will concentrate on it more. We'll try to figure out things. I'm sure there is a difference in the fMRI activity. But as I said, I'm not a neuroscientist.
Thank you for the talk.
By the way, I do want to say one thing though. Even in the case of the encoder and decoder, those are person-specific. Okay, so if a person has never seen anything from the visual world, and will concentrate, the encoder and decoder will be adapted to that particular person. Okay, again, since the fMRI is different from one to another, it's trained per person on fMRI voxels that are the high signal-to-noise ratio for that particular person. Okay. One of the things we're looking now is whether we can generate a universal encoder and decoder by combining information from multiple brains. But that's beyond what I know now.
Thank you for the talk. It was very inspiring. I'm going to ask a similar question to what was asked yesterday. Is doing mind reading ethical? Because there's a lot of nefarious things you can do with these techniques, it seems like. So why? What's the reason why you want to do this?
So I gave the motivations for, first of all, the curiosity. That's my own basic motivation. I like to solve riddles. But there are good motivations for doing that. As I said, communicate with long-term patients. There are many people who cannot communicate. ALS patients, or turns out that some people in coma are completely conscious, but they cannot communicate, and we don't even know that they're conscious. There was a coma patient who was a tennis player, and they put her in an fMRI machine and asked her to imagine that she's playing tennis, and they could really see her motor area being activated. And they asked her to do various things. She was fully conscious. She was like a vegetable. Nobody could tell her. So it would be great if we could communicate with such people. Of course, communicating with them would be more relevant with speech than with images, but that's a very good motivation. Regarding danger, right now with fMRI, for example, with the images, you cannot do this without the collaborating with you. They really have to focus on the image, and then they have to do it several times. If they take the image multiple times and average the fMRI, if a person just ignores the image or thinks about something else, there's no way you can do these kind of things. So currently, there's no real danger. Thoughts don't float in the air. Okay. And of course, you can always ask whether advancing technology is dangerous. That's a general question. We have to do this, and we have to be careful on how we do this. You know, in the Industrial Revolution, people thought it would be the end of the world, right? Very dangerous. People would no longer have anything to do. Agriculture and so on. What will people do? Or similarly, when they came out the first time with prints, with actual printing machines, that people no longer had to calligraphy, write things that people thought was the end of the world. We learned how to live with those things. They actually improve their world, but we have to do it in a smart way.
Yes, I find the last thing we have personal. We have tried to read our thoughts.
No, but I don't believe mind reading is a catchy name. I don't believe that we can read minds today without people's collaboration. And I think that thoughts don't float in the air. And if you don't collaborate, there's no way we can read.
Okay, so in view of time, I think we have to wrap up here. So let's thank